In this work, we introduce tactile neural rendering, a novel approach that leverages a generative model to reconstruct a local 3D representation of an object based solely on its tactile signature. The goal of our work is to recover a local 3D geometry of the object that best explains the acquired tactile signature. Our approach leverages a generative model to reconstruct a local 3D representation of an object from its tactile signature, akin to rendering the object as though perceived by a virtual camera embedded at the robot's fingertip. This 3D representation captures the geometry of the object and provides an intuitive, spatially grounded description of the tactile data. By conditioning the generative model on tactile inputs, our method enables a variety of downstream applications, including precise pose estimation and the quantification of uncertainty. To train our model, tactile signatures are obtained from the contact between a visiotactile sensor and different objects with known poses. For each tactile signature, we compute the simulated in-contact object depth, which takes the sensor parameters as input and outputs a rendered depth map of the simulated in-contact object. To train tactile neural rendering, the tactile signatures and simulated in-contact object depths are used as condition and ground truth of a conditional diffusion model, respectively. We demonstrate the effectiveness of tactile neural rendering through two evaluations, analyzing the quality of the generated in-contact object depth images for different data configurations, and using the 3D reconstructions for pose estimation, where we compare our method to a thresholding-based pose estimation approach, and we quantify uncertainty by analyzing the pose estimation error. To analyze the quality of the generated in-contact object depth images, we compare the generated depth images with corresponding simulated data using distance and image similarity metrics. Our method successfully generates in-contact object depth images exclusively from tactile signatures, which can be used for downstream tasks such as pose estimation. To quantify the performance of our estimated poses, we measure the Euclidean distance between the estimated and ground truth positions, rotations, and the unidirectional chamfer distance. We also use the pose estimation error to quantify the uncertainty of the generated in-contact object geometries. To do so, we use a kernel density estimate plot of the pose estimation error for a specific configuration of an object. Thank you for listening. Please visit our website for the paper, the code release, and all the supplemental material.